no problem. No.
Okay, our next speaker is Vincenzo Alba, and he will talk about entanglement and thermodynamics in out-of-equilibrium systems.
Okay, so thank you very much for the introduction, and of course, before starting, I think it's my duty to thank the organizers for putting together this excellent event, and of course for having me here, giving me the opportunity to present my work. So today I want to discuss with you some aspects of entanglement dynamics, actually entanglement and thermodynamics, in out-of-equilibrium integrable models. This is the outline of my talk, and actually the most important goal of this talk is to discuss how the complexity of the quantum mechanical wave function emerges when you take a system and you drive it out of equilibrium. So a disclaimer, this complexity has nothing to do with the complexity that was defined in the previous weeks, so okay. Actually here I use complexity for entanglement, so complexity means basically entanglement. And the goal of this talk is to provide some evidence that it's possible to describe analytically the entanglement dynamics after a quantum quench in integrable models, okay? So the actual goal is to provide explicit formulas for the entanglement dynamics after a quantum quench. And to this goal here, I will combine two results. So one result is was a well-known semi-classical picture for the entanglement dynamics after a quantum quench. So this picture allows you to understand the qualitative behavior of the entanglement in terms of free-like propagation of particles. And then I will combine this semi-classical picture with the integrability. So for integrable models, it's possible to describe analytically the steady state that emerges after a quantum quench. And the combination of these two ingredients will give an improved semi-classical description that I will present. I will discuss in particular the dynamics of the von Neumann entropy, but also I will extend this picture for the Rényi entropies, and I will benchmark it in several one-dimensional integrable models. So the main result is actually contained in this paper, which was published in 2017, and these are other papers where we explore other aspects of entanglement dynamics in integrable models. So, well, I just started, so I think it's a good time to contradict myself, because I said that I'm gonna discuss complexity in out-of-equilibrium systems. Actually, the truth is that if we study quantum quenches, typically there is an emergent simplicity at long times. Namely, in most situations, we can describe the steady state using statistical mechanics or standard thermodynamics. So in this talk, I will consider, let's say, a very large system, which is made of two parts, A and B. So A plus B is a big system, so let's say the entire universe. And then this entire universe will evolve unitarily. Then I will take the situation in which A is much smaller, okay? I will take the thermodynamic limit for the full system, so capital L goes to infinity. And then I will take the limit of L, the subsystem size, going to infinity. At the same time, I will send the time to infinity, but with the ratio fixed, okay? And this will define the scaling limit that I will deal with in the talk, and that allows us to get explicit results, okay? Now, the main underlying question that I will address is, so I will consider this reduced density matrix for my subsystem A, and the main question would be, what is the structure of this reduced density matrix? That is, does it become simple? For instance, does the system thermalize? So, does this reduced density matrix becomes the Gibbs density matrix? Okay, so why do we want to do that? So, as we learned in the morning, nowadays, there are beautiful cold atomic experiments, and the cold atoms gives us the unique opportunity to address the full time dynamics, the unitary time dynamics after quantum quench in isolated systems, okay? So, in order to model these experiments, so the one typically works with the quantum quenches. So what is a quantum quench? So in a quantum quench, one is given an initial state, psi naught, and one is given also many-body Hamiltonian H. And of course, psi naught is not an eigenstate of H. And one can study the dynamics starting from psi naught under this Hamiltonian H, okay? So one can ask questions, for instance, at long times about local observables, okay? Of course, for a generic Hamiltonian, one can construct the time-dependent expectation value of a generic observable, and this is given by this nice double sum, okay? This is an exact result, but however, this sum is somehow horrible because you see there are two indices, and these two indices runs over the full Hilbert space of the system. So there is no hope for a realistic model to calculate this double sum. However, some simplifications can occur in the long time limit, because in the long time limit, one can neglect in this double sum the off-diagonal elements, okay? By doing so, one gets that the time-dependent expectation value of O becomes actually time-independent, becomes stationary. And this is described by this object here, which is called the typically diagonal ensemble, okay? The diagonal ensemble depends only on the overlaps between the eigenstates of H and the initial state, okay? This is a huge simplification. It's an exponential simplification as compared with this double sum. But still, there is too much information in this expression because you have to be able to compute all the overlaps between the initial state and the eigenstates of H. So, an exponentially large number of parameters. However, for realistic systems, for most systems, for typical systems, there is a further simplifications because you can argue that this expression here becomes equivalent locally to the Gibbs ensemble, okay? So basically, if you are interested in local properties of the steady state of non-integrable models, you can describe them by using the Gibbs density matrix, okay? And the Gibbs density matrix depends only on one parameter, which is the temperature, which is associated to the energy density of the initial state, okay? In this talk, I'm not interested in typical models, so I'm interested in integrable models. So integrable models are the defining properties that they have an extensive number of local and quasi-local conserved quantities, which I call I. These quantities commute with the Hamiltonian, commute among themselves. Of course, since there are all these quantities that are conserved during the dynamics, so the system, the dynamics is strongly constrained, and as a consequence, the steady state fails to thermalize. So even if you restrict to local properties, the steady state, the reduced density matrix, is not the Gibbs density matrix, okay? There is a failure of the thermalization paradigm. However, a statistical description is still possible by using this generalized Gibbs ensemble, which was introduced by Marcos Rigol in 2008, but actually was also introduced earlier by Janes in 1957. Okay? Now, this ensemble is constructed by complementing the Gibbs ensemble by adding these extra conserved quantities with their associated Lagrange multipliers beta j. Okay. Okay. And this proposal generated a lot of enthusiasm in the last 10 years, I would say. Now it's basically the debate is settled, and one would say that it's true that if you are interested in local properties of the steady state after a quantum quench in integrable models, you can describe them by GG. So in this talk, I want to take an alternative and useful point of view. So, and the idea is that you can think of this generalized Gibbs ensemble as emerging from a generalized macrocanonical principle, okay? So namely, what I want to say is that if you're interested in steady-state properties of local observables, you can get them by considering a macrocanonical average, and the states that enter in this microcanonical average are in this window here, and the defined properties of these eigenstates here is that they have to have the correct expectation value of these extra conserved quantities, which are set by their value in the initial state, okay, because they are conserved during the dynamics, okay? Now, in this talk, I want to explore whether it's possible using this technology to understand the entanglement dynamics after quantum quench in integrable models. And on the other hand, I want to see if by looking at the entanglement, we can learn something about the steady state and the approach to the steady state, okay? Now, so for this, okay. So I think I don't need to introduce entanglement because it has been introduced many times during this week. So basically, in this talk, I will focus on the von Neumann entropy, which is defined from the reduced density matrix rho A, and on the Rényi entropies, okay, which are alternative measures of entropy for quantum systems, okay? Okay, so here is the first ingredient that I will use in this analysis. So, and this is the so-called semiclassical picture for the entanglement dynamics. So the idea is that when you perform a quantum quench, you are pumping into the system an extensive amount of energy, and this extensive amount of energy has to go somewhere, has to be distributed, and what the system does is to create pairs of quasi-particles uniformly in the initial state, okay? And these quasi-particles travel ballistically in the system, okay? And they entangle larger and larger system, portions of the system, okay? Now, the key assumption of this quasi-particle picture is that only quasi-particles that are created at the same point in space are mutually entangled, while quasi-particles which are created far apart, they are not mutually entangled, okay? Now, if you want the entanglement entropy now at a generic time t, so the problem of calculating the entanglement entropy becomes the problem of following the trajectories of these quasi-particles in the system, okay? So in particular, if you want the entanglement entropy of a subsystem A at a given time t, basically you have to count the number of particles that were created at the same point in space and at time t are shared between A and the rest, okay? So this is not, now it's a much simpler problem, it's just a kinematic problem. So, and if you do this counting, what you get is this formula here, okay? So this formula here has two terms. So one term is this one, which is proportional to time. So it describes a linear increase with time at short times. And then at very long times, what happens is that this term here doesn't count anymore. The entanglement is described by this term here, and this gives a volume law, okay? The entanglement becomes proportional to the sides of subsystem A, okay? Okay. So this formula was invented by Pasquale Calabrese in CAD 2005, and it's very nice because it describes the qualitative behavior of the entanglement dynamics. However, at least at this level, is just a qualitative description, okay? Because you see, this formula depends on two parameters, this function f, which is basically the probability of generating these quasi-particles at t equals 0. And then it depends also on the velocities at which these quasi-particles travel into the system, okay? So, provided that you know these two parameters, this formula becomes quantitative. You can think of applying it to actual microscopic models, okay? However, this program of calculating the velocities and this function f, so far has been carried out only in free models, because in this nice paper, it has been shown that actually this formula is exact in the scaling limit if you perform a quench in non-interacting model, a model that can be mapped to free fermions, okay? The goal of this talk is to extend this result to integrable but interacting models, okay? So in order to do that, I think I have to introduce you to the realm of integrable models, but it will be a very quick and basic introduction. So the only thing that you need to know about integrable models is that integrability implies that there are stable families of single particle-like excitations, okay? These excitations are labeled by a parameter lambda, which is the so-called rapidity, and is the same as the quasi-momentum for free models, okay? Now, a generic eigenstate of the model is characterized by a collection of these rapidities, lambda and j, okay? Now, in this talk, I want to work in the thermodynamic limit, okay? So in the thermodynamic limit, instead of working with the individual rapidities, it's more convenient to work with their densities, okay? So here I define the density of rapidities, rho, the particle density, and the Hall density, okay? Which is the density of unoccupied rapidities. So very much like a free model, okay? You have particle density and the Hall densities, okay? So each set of density correspond to an exponentially large number of eigenstates in the thermodynamic limit, okay? And the number of these eigenstates that in the thermodynamic limit give rise to the same set of densities is counted by the Yang-Yang entropy, which is nothing more than the thermodynamic entropy in the context of integrable models, okay? So, and it can be written in terms of the particle and the Hall densities in this form here, okay? So this is the main object that I need for the following, okay? The Yang-Yang entropy. Now, in another slide, I quickly tell you how you solve quantum quenches for integrable models, okay? So the idea is that if you're interested in the steady state, local and quasi-local properties of the steady state are described in terms of a representative state, a representative eigenstate, which I call macro state, okay? And I call rho n, okay? Now, if you want the expectation values in the steady state of local observables, basically what you have to do, you have to identify this macro state, and then you can calculate them by calculating expectation values of these operators in this representative eigenstate, okay? Now, of course, in the thermodynamic limit, there is an exponentially large number of eigenstates that are all equivalent, so they are all good representative states, okay? and their number is counted by the Yang-Yang entropy, okay? Okay, so the physical idea actually is that if you go back to the macroeconomical window that I introduced in the beginning, all the eigenstates in this window in the thermodynamic limit give rise to the same set of densities and so to the same macro state, okay? Now, the other thing that you need to know is that for integrable models, you can actually calculate this macro state, okay, analytically. Okay, so now I'm in a position of start to make predictions for the entanglement dynamics. So the first thing that I want to address is what is the steady state value of the entanglement entropy after the quantum quench, okay? I told you in the beginning that if I restrict to a local portion of the system, basically, so the local properties of the system are described by the GG density matrix, okay? So a natural assumption, a natural hypothesis that the density of von Neumann entropy in the steady state is nothing more than the thermodynamic entropy constructed from this GG density matrix, okay? So, and this gives me automatically a prediction for the steady state value of the von Neumann entropy, okay? So, but this is important, okay? It's a simple observation, but it has a very important consequence. And the consequence is that now I can fix this function f that is in the semiclassical formula of Calabrese, okay? So this function f is nothing more than the density of entropy in the steady state, the density of thermodynamic entropy, okay? So one parameter of the semiclassical formula is fixed. Now, the other parameter is the velocities of the quasi-particle that travel into the system, okay? So, I mean, fixing these velocities requires much more work. However, the answer is known for local observables, okay? So if you are interested in the dynamics of local quantities, what you can show is that their dynamics is fixed by the low-lying excitations that you construct around the macroeconomical window that describes the steady state, okay? Now, the assumption that I use in this work is that these low-lying excitations are also the excitations that entangle larger generate entanglement during the dynamics, okay? So, and in the Bethe ansatz, there is a machinery for determining these eigenstates and calculate the group velocities of these excitations, okay? Okay. Now, this gives me the full prediction, so let me summarize it. So the idea to calculate the entanglement dynamics is you start from the initial state, you go to the steady state at infinite time. This is represented by a macro state, a thermodynamic macro state. I can construct excitations around this macro state, and then I can determine their velocities. I can feed back this ingredient into the semiclassical form of Calabrese, and this gives me a prediction for the entanglement dynamics. And if you want an actual formula, so this is the formula here, okay? Now, this S is the density of entropy of the steady state, and this V are the velocities of the low-lying excitations around the steady state, okay? Now, I can think of benchmarking this prediction. So, in order to do so, I will consider the XXZ spin chain, so which is defined by this famous Hamiltonian. Okay, here delta is a parameter of the Hamiltonian, and I consider only parameter delta larger than 1. And I will consider quenches from several initial states. Okay, I consider the tilted ferromagnet, which is obtained by taking the standard ferromagnet and rotating it along a certain axis, okay, by a certain angle theta. I will also consider the tilted version of the nail state, which is the state where all the spins are pointing up and down, okay? And then I will consider the Majumdar-Gauss state, which is the state in which sides on nearest neighbor sides are paired into singlets, okay? Okay. Now, so here I present the MRG data. So this is a quench in the XXZ chain at delta equal 2, and the quench is from the nail state, okay? So in this figure, I show the entanglement entropy divided by the size of subsystem A, and I plot it against times divided by L, okay, this rescaled time. Now, these different lines here correspond to the entropy dynamics for different sides of my subregion A, okay? So, and this dashed dot line here is the theory prediction obtained by this analytical formula. Now you see that so if my subsystem is finite, of course there are corrections, but however, upon increasing the subsystem size, this numerical data seem to approach the theory prediction, okay? Indeed, you can perform an extrapolation in 1 over a subsystem size, and if you do that, you get these symbols here. And they are in reasonably good agreement with the theory prediction in the thermodynamic limit. However, this is a first check, a zeroth order check if you want. So I can do better, and the results are shown here. So here I focus only on the short time behavior of the entanglement entropy, okay? At short times, the entropy grows linearly, and here what I show is the slope of this linear growth. And I plot it as a function of time. And all these panels show the results for all the quenches that I can treat analytically, okay? So the quench from the tilted Nel, the tilted ferromagnet, and also the Majumdar-Gauss or diamond state. Now you see, so these curves here are the ITBD data. So ITBD is a numerical method that works directly in the thermodynamic limit, so I don't have finite size effects. However, you see there are finite time effects. So there is a non-trivial evolution at short times. But then at long times, all these curves approach these horizontal lines, which are the theory predictions that I obtained using the Bethe ansatz, okay? This formula here. And this works extremely well for all the quenches that I can address analytically, okay? Okay, so this concludes the first part. I mean, this analysis can be performed not just for the for Neumann entropy, but you can also consider more complicated quantities like the mutual information. So when you calculate the mutual information, now your subsystem is tripartite. So my subsystem A is made of two parts, A1 and A2, and you are interested in the mutual correlation, the quantum correlation, shared between A1 and A2. And I mean, usually you define the mutual information, so which is written here. So the virtue of this combination is that the contribution of the bulk of the two subsystem is subtracted away, and then you have only the mutual correlation between A1 and A2. Okay. Now the extension of the Bethe ansatz results to this mutual information is trivial because the key ingredients are actually the same. So you see the result is given by this formula, and in this formula there is this Sk, which is the same entropy density as before. So this is the entropy of the steady state, and this V of k are the velocities of the low-Lang excitations as before. Okay. And here I show some theory predictions for the quench from the Nel state, the diamond state, and the tilted ferromagnet. Okay. So you see the mutual information is 0, and this corresponds to short times. So, and then the mutual information increases linearly, and this linear increase corresponds when there is a pair of quasi-particles which connect the two regions A1 and A2. Okay. Then the entropy continue to increase, and this corresponds to these two quasi-particles traveling in A1 and A2. And then when there are no more quasi-particles shared between A1 and A2, the mutual information goes to 0, okay? These are the qualitative features. Okay, so this is the theory predictions. You can imagine of checking this with the MRG. However, this is a very hard task because calculating the mutual information in the MRG is very costly, so you cannot do very easily. So here I present some DMRG results for extremely small subsystems. So this is, for instance, two subsystems of length 3 and then length 4 and length 5. And these are the corresponding, the lines are the corresponding Bethe ansatz predictions. So you see, I mean, the qualitative agreement is okay. And then you see that the theory would predict that there is peak, this peak here, and then you see that the numerical data show the emergence of this peak, but the quantitative agreement is not perfect. Okay, but this we think is just due to the fact that the subsystem sizes are too small. Okay, okay, so so far I presented the results for a lattice model. However, you can do the same, you can play the same game for interacting integrable field theories. So for instance, you can produce results for the Lieb-Liniger model. So the Lieb-Liniger is a system of bosons on a ring which interact via this delta potential, and C here is the strength of interaction, okay? So in this figure, I present theory results for the quench from starting from the Bose-Einstein condensate. Okay, so you prepare your system in the BC state, and then you look at the evolution. And these curves here show the von Neumann entropy dynamics for different values of the interaction strength C. Okay. Now the key feature that I want to highlight in this figure is that the Lieb-Liniger model is a model in the continuum, so there is no maximum velocity into the system. And this is the important consequence that the short time dynamics of the entanglement entropy is not linear anymore. Okay. So again, one would like to test these results using numerical methods. However, the problem is that so far there is no efficient numerical method for simulating systems in the continuum. Okay. So now I want to briefly to summarize what we learned so far. So the key idea is that if one is interested in the entanglement dynamics, basically there are two ingredients. So one ingredient is the thermodynamic entropy, that of the steady state, okay? And the other ingredient are the low-lying excitations around this steady state, okay? So, I mean, this framework of ideas that you can describe the entanglement dynamics only from these two ingredients can be applied to, in principle, to any models, both integrable and non-integrable, okay? In this setup, I want to apply this framework to a very simple model, okay? So this is actually a very simple result. So typically one shows the simple results at the beginning. Here I'm going the other way around, okay? So in particular here I want to deal with the system of harmonic oscillators. So these are basically free bosons on a ring, so described by this Hamiltonian, okay? See, here pi and phi are conjugate variables, okay? So this model is free, so by doing a Fourier transform, one can reduce it to a free model, okay? One gets this dispersion epsilon k, which is given analytically here, okay? So in this talk, I want to focus on a mass quench, okay? So I consider the system in the ground state at given value of mass, m0, and then suddenly I change the mass to a different value, m, okay? And then I want to calculate the entanglement dynamics, okay? Okay, so I told you that the entanglement dynamics is entirely characterized by the representative state that describes the steady state, okay? And this, for this bosonic model, is identified by the occupation numbers, by a certain set of occupation numbers n of k, okay? Which you can calculate analytically here. The other ingredient are the quasi-particle velocities, and again, since you know the dispersion, this you can easily calculate, okay? Now, is less than a page calculation to calculate the thermodynamic entropy of this state, and this is given by this expression, okay? Now you have the two ingredients, you can plug in into the semiclassical form of Cardin-Calabrese, and you get this prediction, okay? Okay. Now I check this prediction, okay? So these are numerical data for the density of von Neumann entropy as a function of the rescaled time. And these different curves here correspond to different values of my subsystem size. And this dashed dot line is the theory prediction in the scaling limit, okay? And you see that actually finite size correction are small in general, but then as you they are there, but as you increase the subsystem size, these lines approach the theory prediction, okay? Okay, and these are two different quenches, okay? Now, why I'm showing that, this result, because you might think that the model is free, you can calculate everything, okay? This, however, is not true, because calculating the entanglement entropy in, even in free models can be a hard task. This task has been performed for free fermions, but repeating it for free bosons is much harder, and it cannot be done in an easy way. However, the derivation using the semiclassical picture is straightforward, and it's one-page calculation, okay? So this, I think, illustrates the power of this semiclassical approach, okay? Okay. Now, I want to switch gear, and I would like to extend this analysis to the Rényi entropies, okay? So why do I want to do that? So there are two reasons, at least. So one reason is that if one is able to know all the Rényi entropies for any value of Rényi index alpha, one can in principle extract all the eigenvalues of the reduced density matrix, okay? One gets much more information than the von Neumann entropy. The other reason is that unlike the von Neumann entropy, the Rényi entropies can be and actually have been measured in experiment, okay? So for instance, in this nice experiment in the group of Marcus Greiner, in Harvard, they managed to calculate, to simulate the dynamics of the secondary Rényi entropy after a quench in the Bose-Hubbard model, okay? I mean, system sizes that they can address are very small, but this is very promising, I would say, for the future. Okay, now, how do I calculate the Rényi entropies in the Bethe ansatz? So the idea is similar it's the same that I used for the von Neumann entropy. So local properties of the system are described by the GG density matrix, okay? So the natural idea is that the Rényi entropies, the entanglement Rényi entropies, should be the Rényi entropies that you construct from this GG density matrix, okay? However, there is a crucial difference with the von Neumann entropy, and the difference is that to calculate the Rényi entropies, you have to take the power alpha of the reduced density matrix, okay? And this has the consequence that all the Lagrange multipliers that enter in the GGE, they get multiplied by alpha, okay? Now, if you take this new density matrix, where all the Lagrange multipliers have been multiplied by alpha, and you calculate, for instance, local observables, of course, these are different from the local observables of the steady state, okay? So this implies that if you want to describe the steady state value of the Rényi entropy, you have to change the macrocanonical window, okay? So the macrocanonical window that gives the steady state value of the Rényi entropy is not the same macrocanonical window that describes the local observables in the steady state, okay? Okay. However, you can do this calculation, and then if you do this, you get the Rényi entropies in the steady state are given by these generalized free energies, okay, that you can evaluate in Bethe ansatz. Now, of course, you can make theory predictions. So, for instance, these are the densities of the Rényi entropies for several values of the Rényi index alpha, plotted as a function of delta in the XXZ chain after the quench from the null state, okay? So these are theory predictions. And you can benchmark them using DMRG, okay? So here I focus on the second Rényi entropy only, okay? Again, this is the quench from the null state. These are TDMRG data for the steady state value of the Rényi entropies, plotted as a function of the size of my subsystem, okay? So for different values of delta. So you see, for all the data show this nice volume law behavior for the Rényi entropies, and these dashed dot lines are the theory predictions that you get from Bethe ansatz, okay? And you see they perfectly well describe the numerical data. So now you see that there is a final ingredient missing. So how about the full-time dynamics for the Rényi entropies, okay? So here the discussion will be very short because the result is that we are not able to calculate the full-time dynamics. We can only calculate the steady state value of the Rényi entropies. And if you want, this is due to the fact that to calculate this Rényi entropies, we had to change this microcanonical window, okay? Now the consequence is the following. So if you look at the density of the Rényi entropies, so this Sn alpha lambda, and you plot it as a function of the quasi-particles rapidity lambda, you see that this density is not positive definite, okay? There are some values of lambda for which these particles would have negative Rényi entropy, okay? And this is not possible, okay? It's clearly an artifact of the calculation. Of course, if you perform the integral, you get a positive value because the steady state Rényi entropies are positive, as they should. So there is a way out, of course. I mean, because in our analysis, we calculate the Rényi entropies by performing this integral, and we have these densities here, okay? Of course, you can always add the function whose integral is 0, and then the steady state value of the Rényi entropies would not change. However, this would make this function positive, and then you can imagine of doing the semiclassical picture. So far, however, there is no recipe on how to calculate this W, so this program we are not able to perform, okay? Okay. So I think with this I want just to conclude. So I hope I convince you that it's possible to describe analytically the entanglement dynamics after a quantum quench in integrable models. And this has been possible by combining a well-known semiclassical picture for the entanglement dynamics with the integrability-based results. And finally, I think I would like to stress an important feature of this analysis that is the following. So in our work, in our analysis, basically the only ingredients that we used to describe the entanglement dynamics was the steady state and the low-lying excitations around the steady state. So there was no need of exploring the full spectrum, okay? And with this, I think I would like to thank you for coming and for your attention.
Questions?
Yeah.
I think I can speak out loud.
Yeah, yeah.
So you showed us a nice curve of the mutual information being non-monotonic with a function of
Yeah.
time.
Yeah.
So do you have any physical explanation of why there's this maximum?
Yeah. So it's this is actually a very good point that I would have liked to stress, but due to the amount of time I couldn't. So if you go back to this, if you go back to this figure, Okay, so I mean the generic feature, if you have only one type of particles traveling at a given velocity, the generic behavior of the mutual information that you have a linear increase and then a linear decrease and then the mutual information is zero. Okay, if you have, but in a realistic model, you have a dispersion, so you can assign different momenta at the quasi-particles. So typically this gives you a linear increase, which corresponds to the fastest particle, and then the linear decrease is smoothened out because you have the contribution of the other quasi-particle coming. Okay. Here, however, there is another funny feature. So if you look at this quench here, so actually there is a second bump. Okay. And this is due to the fact that in generic integrable models, you can have different species of quasi-particles, so which correspond to different bound states of different size. So this behavior here correspond to the so-called one strings, which means the magnons. And then this bump here correspond to the two particle bound states, which typically travel much slower, okay? So this is actually nice because, I mean, by looking at the mutual information, you can think of at least performing a spectroscopy of the post-quench Hamiltonians, okay? You can read out in some way the quasi-particle content, okay? No, it's just the kinematics. When you don't have any more quasi-particle, you have a quasi-particle. So the entanglement is generated by quasi-particles that are put at the same point in space, and then for a certain time they touch the two subsystems. When this quasi-particle go away, the entanglement is the subsystems are not entangled anymore. I mean, you have to convince yourself. You have to think about the kinematics, but you can. It's okay. Yeah, okay. It's just for technical reasons that the steady state description in terms of the Bethe ansatz is a bit easier if you go delta larger than 1. Actually, I have results for delta equal 1, so you can do the same analysis at delta less than 1. Yeah, but I never did it, so it's just because extracting the root densities that describe the steady state is a bit more involved, but in principle you can do it. Yeah. Sorry, what?
How do you again justify only using the low energy states?
I'm not using low energy states. I think, okay, your question is a very good question, so because it allows me to stress an important point. So this analysis has nothing to do with the low energy. So when I talk about excitations, it is excitations in the middle of the spectrum. Okay. Oh, okay. As I said, I mean, for local observables, you can actually show it. So if you do, you can write the formulas for the dynamics of local observables, and then you can show that, I mean, low-lying excitations are enough. I mean, this is reasonable for sure at long times, right? Because long times it corresponds to small energies around the steady state.
Maybe it's because you are taking the average.
I'm not taking any average. No. Sorry? Yeah, okay. I think, yeah, okay, maybe. I think the answer is that if you look at the matrix elements, they can be very different. But if you look at thermodynamic quantities like the entropy, I think the fact that you move away a bit from the steady state doesn't change much.
Any other question? Okay. If not, let's thank the speaker again.
Sorry, a quick announcement. Tomorrow we cancel the first talk because the speaker could not come. So